In this video, we will talk about hypothesis testing for numeric or quantitative variables. The example we'll look at is based on a 2004 study that examined mercury accumulation in largemouth bass taken from a sample of 53 lakes in the state of Florida. If mercury levels exceed 0.5 parts per million, then there are reasons that we might be concerned about the environmental conditions in the lakes. The legal safety limit in Canada is 0.5 parts per million, although it is 1 part per million in the United States. The histogram shows the distribution of mercury levels for the 53 lakes in our sample. We see that most commonly lakes have mercury levels between about 0.1 and 0.5 parts per million, but there are some lakes exceeding 0.5 and some with mercury levels above 1 part per million. In the sample of 53 lakes, the mean mercury level was 0.527 parts per million with a standard deviation of 0.341. The parameter that we're interested in this situation is the mean mercury level for all lakes in Florida. We want to make conclusions about all of the lakes, not just the 53 in our sample. Our null hypothesis is that the mean mercury level for all lakes is 0.5 parts per million. The alternative hypothesis would be that the mean mercury level exceeds 0.5 million when we consider all lakes in Florida. The quantity we saw in our sample statistic, is X bar equal to 0.527, the mean mercury concentration level in our sample of 53 lakes. Note that we use different symbols in this situation to represent the parameter of interest than what we've used so far. In this case, we use the Greek letter mu because this represents a mean rather than a proportion. Similarly, we use X bar to represent our sample statistic because we're interested in the mean mercury level instead of a proportion as we've seen before. This situation is different than the problems we've looked at so far in that we've thus far considered categorical variables, things where the result could fall into 2 or more categories, such as whether or not a dolphin picked the right button, whether a chimpanzee picked the correct photo, whether or not people were comfortable riding in self-driving cars. Those were all examples of categorical variables. In this new question, mercury levels are not categories, but rather numeric values. Such variables are called numeric or quantitative. This table summarizes some of the differences between categorical and quantitative variables. In categorical situations, the data are categories, while in quantitative situations, the data are numbers. In a categorical situation, we would be interested in an unknown long-run proportion as our parameter of interest. For example, the proportion of all Americans who favor riding in self-driving cars. In a quantitative situation, we're interested in an overall mean, such as the mean mercury level in all lakes. Likewise, the sample statistic will be a proportion which we denote p hat in a categorical problem, or a sample mean denoted x bar in a quantitative situation. We've done extensive work with simulating null distributions for categorical variables using coins, dice, or technology. In quantitative situations, we could also simulate the null distribution, but that requires a different technique known as bootstrapping. While this technique involves sampling from the data itself and has grown in popularity recently, we will not discuss bootstrapping in this video. Instead, we'll rely on a theory-based calculation similar to what we saw for z-scores in the categorical situation. Just like with categorical variables, assuming that it's reasonable to think that our distribution is roughly symmetric and bell-shaped, we can calculate a standardized statistic. In this situation, we'll calculate the standardized statistic by taking our sample mean and subtracting the value of mu from our null hypothesis, and then dividing it by the sample standard deviation over the square root of the sample size. This quantity in the denominator, s over the square root of n, is known as the standard error for the sample mean. We call this statistic t. The reason for that is because this statistic, under certain assumptions, is known to follow a t-distribution. When you look at the picture, the t-distribution looks a lot like the normal z-distribution that we've seen before. In fact, a t-distribution is also a symmetric bell-shaped curve, and we can apply many of the same rules that we used for a normal distribution. As our sample size gets larger, the t-distribution begins to behave even more and more like a normal distribution. If we calculate a standardized t-statistic more extreme than 2 or negative 2, we can interpret that as strong evidence against the null hypothesis. In the Florida Lakes example, if we calculate a test statistic for our null hypothesis that mu, the mean mercury concentration in all lakes, is 0.5, we calculate that by taking our sample mean, 0.527, minus 0.5, and dividing it by the sample standard deviation over the square root of the sample size. In this case, that t-statistic comes out to be 0.58. When we picture where that lies on the t-distribution, we see that it's fairly close to the center of the curve. This tells us our result is not that extreme and would not be unexpected in a situation where the mean mercury concentration in all lakes was 0.5. Therefore, our data are consistent with the situation where the mean mercury concentration in all lakes is 0.5. This is a plausible outcome. This is a plausible situation. We can also compute a p-value for this test using R, the t-test command. I specify the data set with my values in it, in this case from the Florida Lakes data set, the value of mu from the null hypothesis, and in this case our alternative is greater since we expected that, or we suspected that the mean mercury level might be greater than 0.5. We see that the p-value in this test comes out to be 0.2822. Because this value is quite large, we don't reject our null hypothesis. There is approximately a 28% chance of observing a sample mean as large as 0.5 parts per million if the true mean mercury level concentration for all lakes was really 0.5 parts per million. We do not have sufficient evidence to conclude that the mean mercury concentration for all Florida lakes is more than 0.5 parts per million. As we saw with categorical variables, there are also conditions for when it's appropriate to use a t-distribution for quantitative variables. This approximation is reasonable as long as one of two things holds. Either the data in our sample should be roughly symmetric, or our sample size should be fairly large, we'll say greater than or equal to 20, with the data not being heavily skewed. If I go back and look at our data from our sample, the distribution in our sample does not really look that symmetric, so I would probably not conclude that the first condition is satisfied. But because we have a sample size of 53 and our distribution is not heavily skewed, the second situation appears reasonable. Therefore, we can go ahead and do the test that we did and expect a reasonable outcome via the second condition.